Right. Let me remind you where we are now. So it's this new chapter 1.3. Dimer models on toroidal bipartite graphs. So I think last time I wrote toric. That's a wrong translation from the French. It's toroidal in English. And I could double check because I went online and I checked, yes, I had written toric, so that's wrong. Toroidal, meaning embedded in the torus. And so it was this first paragraph on the height function. And I had just explained this gauge invariance story, which was basically saying the Dimer measure, the Dimer model, is invariant under the action of the gauge group which are functions, real positive valued functions on the vertices on the set of weights given by, so it's a very, I did this computation last time. It's very easy to check that it's invariant. And therefore, the issue is that we have, so to speak, too many parameters. So maybe the way of parameterizing the Dimer model by these edge weights is not good because there are so many edge weight systems which will give you the same model, all the ones that are invariant by the action of this group. So the orbit, if you take any edge weight, and then you act in any way by this group, you will not change the model. Okay, so the question was, how can we have some better weights, parameters, let's say. And so I had said, you can answer this question if the graph is bipartite and if it's embedded in the surface. And so to do this, to explain this, I will need just a little bit more homology. So this will be, don't worry, it's not going to be a whole lot more. So I'm just going to speak about a little more homology. So again, we take the same setting that we always had. So we take G, a graph that is embedded in a surface sigma, which I will assume, as always, to be closed, oriented, and connected. And as always, I want the graph to approximate to the topology of the surface well, so I want that the complement of the graph is disks, topological disks. Okay? So remember what we had done. We had worked over Z2. And what we had found some kind of, so it's called the chain complex. So really so we could I had written just C2, C1, etc., but we can write it like this. Yes. I mean, you're right. No, you're right. You're right. So here, I mean, really it's the C complex. So it's, I can write sigma if you want. Okay. And we had these boundary maps, remember? Okay. And the question was asked when I was talking about this was, don't you need to orient stuff? I think it was Maxime who asked the question. Don't you need to orient stuff? So the point is, if you're working over Z2, then plus is equal to minus, well, there is no sign, plus 1 is minus 1. And so you don't need to orient things, and things are very easy. And that's what I had explained 1 month ago or so. So actually what happens now is, so I will need to have a slightly more subtle version where you do orient things. And this corresponds to when you look at homology with any coefficient that is not characteristic 2. So now we will work over R, for example, and, or let's say, or Z, or anything, basically. So we need to orient our edges and vertices and faces, everything, to orient everything, let's say. So in this case, it's still not so complicated. The general theory can become a little bit annoying, a little bit tedious. When you need to orient objects of arbitrary dimension, it becomes a little bit tedious. Here it's still okay, so let's do the following. So let us fix an arbitrary orientation on each edge of G, and also on each face. But maybe on each face we want them to be coherent. We don't need this, but really, now you have the faces on the surface, so you have a global orientation on the surface, so maybe you want the faces to be oriented in this coherent way. It's not necessary, but let's do this. And say in orientation on each face of G embedded in sigma. And let's say we'll picture it counterclockwise, okay? Now let's define our set. So I will write C0, so let's write sigma for Anthony. This will be, so the R vector space, the real vector space, with bases, the set of vertices of the graph. Then I will write C1, the R vector space with bases, the edges, but now we remember that each of them is oriented. And C2, faces, same thing, each of them is oriented.
So the singletons are not oriented?
The vertices, yes, they are oriented, but what is an orientation on a point? It's a sign, right? So here, actually, they are oriented, but I don't want to say that I fix an orientation on the vertices. I just say, you just take plus everywhere, okay? So if you want, you can think of them as oriented, but okay. Okay. Now, what do I need to extend the theory? I need to define what are the boundary operators, so D2 and D1. Now, so finally, set. So I want to define D2 on this set here. So that's the real edge space with bases, the oriented faces. So I just need to define it on the elements of the bases, that is on a face. So if I have a face like this, so it's oriented this way. So of course, what I want to define this as this oriented edge plus this oriented edge plus this one plus this one plus this one. Okay, and then you extend it linearly. And then if you have an oriented edge like this, you want to define its boundary as W minus V. And then you note that the only thing we need to check now so that everything works is that when you compose two of them, you get 0. So note that, so let's see if I compose D1, D2 of a face. Well, you see it works. Now, you see you do the D2, the face, you get this one, and then you have this minus this plus this minus this, and you have this telescopic thing. It works. So D1 composed with D2 is equal to 0. And actually, if you take any DI, because DI plus 1 is equal to 0, the other ones are trivial. So we can define HI of sigma with real coefficients as, so the kernel of delta I over the image of delta I plus 1. And this is the ith homology space or group. Sorry. Of sigma with real coefficients. And now the fact that makes the whole theory worth it is that in the setting that I had given here, we have that H0 is always one-dimensional, H1 is always 2G dimensional, where G is the genus of the surface. And H2 is also one-dimensional. And of course, you can do the same theory over, so actually over any abelian group, but the only other I think we will use is Z. Okay. Maybe just as a side remark for general culture, here in this example you might think that it's completely useless to consider to change the coefficients, because when we did it over Z2, we had Z2 power 2G, Z2 over R over Z, it gives the same thing. So in case of an orientable surface, it's true that you don't have more information changing coefficients, but it's not true in general. So even if you look at non-orientable surfaces, for example, you take the Klein bottle, if you look at the Klein bottle, you take R coefficients, you will get 0 for H2. Klein bottle with Z2 coefficients, you will get Z2. So it's just to say that it does make sense sometimes to change coefficients. You do get different information. Okay. The point here, of course, is that it does not depend on the graph that you have chosen to approximate your surface. Good. Okay. So now I will start with the planar case. I will explain everything in detail for the planar case, and I will just tell you afterwards, at the end of the class, what you need to change if you're working in a general surface. So, okay. So let G be a bipartite graph. And so we're going to assume that it's embedded in the plane. And I'm going to assume that it's connected in the plane, so R2. And of course, if I want to be in the setting of the theory before, I want to look at this as R2 embedded in the 2 sphere, which is the surface of G is 0. Okay. So now what happens? If it's bipartite, it means that each edge, so there is a very natural orientation that you can set on each edge, right? So let's say, so I'll have to follow my notes because otherwise if I mess up this one, it's going to be really annoying. So I'll say from white to blacks. Okay. So you have the white vertex, the black vertex. You can always fix one orientation that is coherent to say, let's just go always from white to black, okay? So the bipartite structure induces an let's say, so we call it a bipartite orientation. Say, always from white to black. Of course, you could have chosen the other one. There is absolutely no reason to choose this one, but you just fix one and then let's say it's this one. From white to black. Okay. On top of that, of course, since the graph is embedded in the plane and you just make an orientation of the plane, each of the faces is also oriented, okay? So, of course, each face is oriented in a coherent way. So, as I said before, say, let's say counterclockwise. We picture it counterclockwise. Okay, so now let's consider an arbitrary element phi of C1. I really want to write G, that's why I was. So now because of Anthony, I'm stuck with this sigma. That doesn't make sense anymore. So anyway, you see what I mean. Now you just look at something here. So how is it written? So it means it's an element of the form sum over all the edges, some real coefficient here times the edge. Okay. Again, the edge is always oriented this way. Okay, so now let's compute its boundary. So the boundary of phi, so it would be the 1 boundary. What is it? So it's sum boundary of E. Now boundary of E so boundary of E by definition it's B minus W. So now what do I get? If I can sum over all black vertices minus sum over white vertices, and here I get the sum over all edges that are adjacent to B, and here the sum over all edges that are adjacent to W. Sorry, it's not very readable. Okay, and so the concept that will be important now is the concept of a unit flow. So I already introduced it in the homework exercise. A unit flow is an element of this form such that its boundary is exactly sum over black vertices minus sum over white vertices. So you see, it exactly means that when you look at any black vertex, well, if you look at any vertex, you sum the coefficients that are around, you always get 1. Okay? For example, if you take M, a perfect matching on the graph, this gives you phi M, the sum of all edges in your perfect matching, and this is a unit flow. Right? This is really the definition of perfect matching and of unit flow. Every vertex is adjacent to exactly one edge, so you just set equal 1 on this edge and 0 everywhere else, and okay, when you sum up around each vertex, you get 1. And then it was this, I think exercise 4 in homework 7 that actually now we just proved that if there is a perfect matching, there is a unit flow. Actually, it goes the other way around. If there is a unit flow, there is a perfect matching. So there is a perfect matching if and only if there exists a unit flow. So why do we want to fix a unit flow? Well, the point is, bless you. So from now on, we're going to fix one unit flow. So fix a unit flow phi 0. Now what we will do is we will use this as some kind of reference flow, and we're going to measure the perfect matchings and the corresponding unit flow. We're going to measure the difference of these two. So now, given any perfect matching, consider the difference phi m minus phi 0. So this is an element in C1. Now, what can we say about this? We have, if we take the boundary of this element, what do we get? The boundary of phi m minus the boundary of phi 0. And of course, both of them are unit flow, so their boundary is going to be the same. So what we have here is sum black vertices minus sum of white vertices minus the same thing. This is 0. Right? So this means that phi m minus phi 0 belongs to the kernel of delta 1. And now we are on the plane, so we are on the plane, meaning h1 of sigma is 0. We're in the genus 0 case. h1 is the kernel of D1 over the image of D2, meaning the kernel of D1 is equal to the image of D2. So it means, finish here, there exists some element which I want to write hm, depends on m of course, in C2 such that delta 2 of hm is equal to phi m minus phi 0. So what is this element? So hm is of the form it's a sum over the faces of the graph of this form with hm of f a real number. So basically it assigns to every face of the graph a real number. And this hm is called the height function associated with the perfect matching m. So hm is the height function corresponding to or associated with this perfect matching. So it means to each face you give a real number. So we had started with a perfect matching, and to this we associate now a function on the faces. You give a height, a real number to each face. So the first question is it unique? So is it uniquely? Now we have an hm here, but there is no unicity here, no uniqueness here, a priori. So let's see. So let's see. Let's assume that we have another one here, and let's see what happens. So assume we have some hm prime with the same property, with d2 hm prime equal to phi m minus phi 0. So then what do we have? We have that d2 of hm prime minus hm is equal to d2 hm prime minus d2 hm. That is something minus the same thing, that is 0. So it means that hm prime minus hm belongs to the kernel of D2. Now, unfortunately, I don't have any longer my chain complex, but the kernel of D2 is equal to the kernel of D2 over the image of D3 because D3 is 0, and this is equal to H2 of the surface with real coefficients, and we had just said this is equal to R. This means that actually it is not unique, but it's unique up to overall additive constant. So hence, HM is uniquely defined by M up to a global, up to an additive constant. So what do you do to get rid of this indeterminacy? You just say, okay, you fix the height of some face to be 0. Okay, and then we're good. So let's say you take the outer face, I don't know, and you said this is equal to 0, and then we're good. Okay, so let us say that HM of F0 is equal to 0 for some fixed face. For example, since if we have a finite graph on the plane, we just say it's the outer face. For example, the outer face. And then unique. And now I just want to, so it means we have a map going from perfect matchings to height functions, and I just want to show you that this map is injective. So furthermore, if HM is equal to HM prime for two perfect matchings here, then what do we have? Then 0 is equal to HM prime minus HM. So I'm just going to look at the boundary of this. So this is the boundary of HM prime, that is phi m prime minus phi 0 minus phi m minus phi 0. So we have that, in this case, phi m is equal to phi m prime. But remember, this is the sum over all edges of the matching. So if these two are the same, it means that the matchings are the same. Okay. So let me just make a little summary of what we did so far. So for any fixed unit flow phi 0, we have an injective map which goes from the set of perfect matchings on the graph to the set of height functions. So these are functions h from the faces of the graph to R, such that they take the value 0 on some fixed face. Okay, so one of the things now to keep in mind of this little discussion is basically if your graph is bipartite, then you can orient things. If you can orient things, it means you can take homology with any coefficients you want, and then you can look at height functions, for example. If it's not bipartite, there is no way to do this. Okay, so of course the problem here, well, I don't know if it's a problem, but the point is that it will depend, of course, on phi 0. So what will you take for phi 0? In general, you don't have a natural choice for unit flow, but there are some cases that are very beautiful where you have very natural choices. And so I want to explain a couple of examples here. So in general, so this map will of course depend on phi 0. In general, there is no natural canonical, let's say there is no canonical choice. But sometimes there is. So let me explain this. I'm going to consider two examples. First example, the hexagonal lattice. So consider so again, I want to look at my notes because I don't want to invert white and blacks. By the way, I did this in the homework assignment. I switched white and blacks compared to the conventions in this class, but it should be okay. So actually, I corrected it by hand here, but okay. Consider the hexagonal lattice in the plane, embedded in the plane. So of course it's bipartite, so everything works, but there is something nicer. So let me just, okay, so that's supposed to be white, it's supposed to be black. So of course here you do have a natural unit flow. You see which one? So it is bipartite. And admits the natural do you see which one? Yeah, that would be one. No, I'm thinking of another one. You're right, so that would be another natural one. There is a nicer, well, there's the one that gives a nicer geometrical understanding of the height of the corresponding height function. So it's just to take 1/3 the sum of edges. Right? You just set 1/3 everywhere. So if I take the conventions, the bipartite orientation was going like this. Just set 1/3 everywhere. Right? That works. Now I'm going to show you what is the corresponding height function. It's very beautiful. So the corresponding height function is given as follows. So I will simply look at a neighborhood, a little neighborhood of a dimer, of a matching. So I just take this edge to be an edge of the perfect matching. Okay, now I want to consider phi m minus phi 0. So on this edge, and I want to just keep write again the bipartite orientation just so I don't forget. So what is phi m minus phi 0? Here, on this one, you have 1 minus 1/3, right? So you have 2/3. And on all the other ones, you have minus 1/3. Now let me just think about the rule. If I have some, so I have my edge like that, and let's say that the value here is delta. So the way to compute the height function is if you have value a here, if the height function here has value a, here the value should be a plus delta. Right? Because then when you make the sum of the boundary of this height, you'll have the face is oriented like this. So here you'll have a contribution a plus delta on this edge. And here it's oriented like this. So you'll have a contribution minus a. So when you look at the overall contribution on this edge, you have a plus delta minus a, so it's delta. Okay? So reverse engineering it, it means when you have a value a here on this side of this edge, if you pass it like this, then you'll have value a plus delta here, if the value of the flow here is delta. So let's make this thing here. So let's say that the value here is a. So maybe I'll just take another color. Let's say that the value here is a. So here I'm passing it with the white one to my left. So here it's going to be, so I have to add this. So I have a minus 1/3. Here I'm passing it with the white to the left. So I have to add 2/3. So I have a plus 1/3. And indeed it works. Here, if I go here, I have minus 1/3. And here it's the other way around. If I go here, I have to add, well, I have to subtract minus 1/3. So I have to add 1/3, a. And here it works as well. So here I just fixed some value a here on this face, and this is the way to get the value of the height function on the other faces. Okay, so of course, the way you want to think about this is, well, you can think about this as a function taking values on the vertices of the dual triangular lattice. So this height function can be thought of as a function on the vertices of the dual triangular lattice. So here let me just draw the corresponding triangular lattice. Okay, and so this is the white face. And so the values are a. And maybe I'm going to multiply everything by 3. So to have integer values. So that's a plus 1. Oops. A minus 1. A. Okay, but now remember that perfect matchings on the hexagonal lattice correspond to lozenge tilings on the dual triangular lattice. So correspond to lozenge tilings of the triangular lattice. So now you have a rule that tells you each time you have a lozenge in your tiling, each time you have a lozenge with this, so each time you have a lozenge with the white part here and the black part here, then the rule you have to follow is this one. Okay. Why is this very beautiful? It's because actually if you make a drawing of the lozenge tiling, what you see is like what you see is something like cubes that are piled up together, and this height function that you will have here is exactly the height of the corresponding cubes, or the corresponding vertices of these cubes. So I'm just going to make a little drawing. So this height function let's say corresponds to the discrete surface interpretation of lozenge tilings as explained in the introduction. I don't know if you remember, the very first class I had given this, I had said this, if you look at dimers on the hexagonal lattice, actually it corresponds to rhombic or lozenge tilings, and actually you can see this as a random discrete surface, and this is now the geometric explanation. So maybe I'm just going to make one illustration. So, it's always such a mental effort to copy a bipartite structure from the sheet of paper to the blackboard, because you have to inverse everything, I think. Okay. So let me take this one as an example, and let me give the values of the corresponding function. Let's say that this here is 0, then what you get is, so I multiply everything by 3. 1, 0, 1, 0, and 2. You can check that it's, so the rules I gave here give you exactly this. And so now I want to draw the corresponding rhombic tiling. Okay, so now I look at the triangular lattice and I draw a lozenge. It's along each dimer. And so you see that, well, I guess you see it. If you put a cube like this, that's the height of the corresponding vertices. Okay, so I don't want to say too much more about this, but actually, so this story of height function was actually introduced by Bill Thurston in 1990, and with this, he gave an extremely nice characterization of the domains in the plane that are made up of equilateral triangles. So there are domains in the triangular lattice that can be tiled by lozenges. It's extremely nice. So maybe just as a remark, so this was introduced by Thurston in 1990 to study which domains in the plane are tileable by lozenges. So see exercise 3, exercise 2 in homework number 8. So it's really extremely nice the way so actually in the homework you're going to prove the whole theorem. It's extremely nice. The way it works is that, well, let's see. Here, you see that each time, so let's say that we're around a white vertex. And now let's orient the edges of the corresponding triangular lattice counterclockwise around the white vertex. So each time you have a white vertex, you go counterclockwise. And each time you have a black vertex, you go clockwise. So I missed, so yeah, I said one word for the other, but I guess it's okay. So here, counterclockwise, okay, because I use my left hand. Right, okay, now you see that each time you go around, you look at the height function, each time you go in this direction here, you either go up by 1 or down by 2. Okay. And in the other, around the black ones, it's the same thing. So here you go up by 1, down by 2. So now you fix a domain in the plane. So R, let's say it's a simply connected domain. Made of these triangles. And so let's say, I'll fix one. And let's say let's say that this one is white, this one is black. So I orient the edges as I just said. So it goes like this. And I fix a value, let's say 0 on this one. Okay, so I have my simply connected domain. I have this rule of going clockwise around blacks, counterclockwise around whites. And so this gives me an orientation on the boundary of the domain. And I will just say, okay, each time I go around the boundary along an edge, I just make +1. Okay, so here I have +1, here -1, +1, -1, +1. First thing that is very easy to check, you will do it in exercise. If you go around the domain like this, it gives you a well-defined height function around the boundary if and only if it encloses the same number of white and black triangles. So that's easy. So let's assume that indeed it contains the same number of white and black triangles. If you don't have the same number, then of course your domain is not tileable by lozenges. Okay. So let's assume that this works. So then you have this height function h on the boundary. And the theorem of Thurston is, so the domain R is tileable if and only if for any two vertices on the boundary, we have that h of, let me just make sure I don't mess it up, h of w minus h of v is less or equal to the distance between these two, where here we have to be a little bit careful. This is the length of the minimal oriented path, oriented with these orientations here. This is the length of the, so or minimal length of an oriented path from V to W. So in this case, for example, of course it works because, well, you see, if you take, so anyway, it works here. The difference is never more than 1, and the distance here will be 0 or 2. Okay. So of course this domain is tileable, but that's a general theorem. It's very nice. So this is the kind of historical origin of this concept of height function. And I'll just, okay, I will make a break now. And after the break, I'll just tell you one word about the square lattice. So on the square lattice, you can do the same thing, of course, because there you can take 1/4 of the sum of all edges, and then you can look at what happens. Everything works completely fine. Actually, the theorem here works as well, but it's just this illustration will not be as nice. So here, for the square lattice, you don't have this beautiful picture where you have cubes that are accumulating. It's like a roof tiled by tiles that are a little bit crooked. It's going to be a little bit weird, you'll see. Okay, let's make 15 minutes break. Okay, so as promised, let me give you a second example. I will not give all the details here. So consider the square lattice. So it is bipartite and planar, so that's fine. And it admits the canonical or the natural unit flow phi 0 equal 1/4 sum of all the edges. So I will just give you the corresponding rule around the dimer. So the rule for HM is given as follows. So again, let me just make sure I get the bipartite structure right. So let's say that I have a dimer here on this edge. So the bipartite structure, the orientation always goes this way. And so if I look at phi m minus phi 0, I will have minus 1/4 on all of the edges. And plus 3/4 here. So the corresponding height function, I'm going to have a here. So it's a minus 1/4 here, a plus 1/2 here, a plus 1/4 here, and going around here, I have a and a plus 1/4. I think that's correct. Yeah, it seems so. So of course, you can look at this as corresponding to a function, a real valued function on the vertices of the dual square lattice. So this would correspond to a function here. And so I would have the values, I multiply everything by 4. So I have a plus 1, a minus 1, a plus 1, a plus 2. And so it gives a height function interpretation of domino tilings. right? Remember the perfect matching on the square lattice, they correspond to domino tilings. But of course, now here this picture is not as easy to understand. Again, here, you had this picture, each time you have a rhombus, you have heights that vary 0, 1, 1, 2, and it's kind of natural. If you have a lozenge, you can put it in some way such that it really realizes, you can embed your lozenge in the 3 space so that the height of the corresponding vertices are really like this. Here in this case, if you want to embed a rectangle in the plane, embed a rectangle in the space so that the corresponding vertices have this height, you cannot do this with a rigid rectangle. You have to twist them a little bit. So for this reason, the corresponding geometrical picture for domino tilings is not as easy to imagine, to understand. But it can be done. Okay, and so here, see homework number 8, exercise 3. Okay. Good. So now let's come back to what we had started with. So now what I will do is I will translate the Dimer measure, the Dimer model, from perfect matchings, Dimer configuration, to height functions. Okay, I will translate this measure, and we're going to see that we have some natural parameters that come, and we'll see that we have exactly the right number of parameters that come. So the parameters given by edge weights were too many, and then we'll see that now we're going to have the right number of parameters. So let us translate the Dimer model from M of G to height functions. Okay. To do so, I fix edge weights and set new beta, so beta is for bipartite, going from set our oriented edges to 0 infinity, and I write it this way. It will be the weight of the corresponding edge if the edge is oriented from white to black, which was our bipartite orientation, and the inverse in the other case. And I will extend this multiplicatively. Okay. For any fixed oriented face F, consider the associated, it's called the volume weight, QF, which is defined as follows, defined by QF of, well, QF is equal to nu beta of the boundary of F, meaning product over all the edges so oriented edges in the oriented boundary of F of nu beta of E. So just to make sure that we agree on what I just defined, let's imagine I have a face like this. It's oriented. I look at the boundary. Let's say that I have E1, E2, E3, E4. So here in this case, QF will be equal to what? So for E1, I go from black to white, so it's the inverse. So I'll have nu of E2, nu of E4 over nu of E1, nu of E3. And maybe I can already make a couple of remarks. So these will be the weights, the new weights that will be the best way to parameterize a Dimer model. So first notice that these weights are invariant by the gauge transformation on nu. So by gauge transformations right? Is this clear? Well, you see, if I multiply all the weights adjacent to a vertex by something, well, on one hand I will multiply the numerator, the other one. Okay, it's fine. So this is clear. And now, how many parameters do I have here? So note that I'm not completely free. I have one constraint on these weights. It is that if I take the product over all the faces on my surface of all these weights, I get 1. Right? Because if you think about it, you multiply everything. Each edge is counted once in one direction. Okay? So these weights have the constraint that the product over all the faces of this weight is equal to 1. So we have really, the number of free parameters is really given by this. And so actually I can finish this discussion before giving the translation to the Dimer model to high functions. Actually now I will show you that this is exactly the right number of parameters. So now let's just think for a second. So we have, the edge weight parameterization has a number of edges parameters, right? Let's say, parameters. Now the gauge group has this number of parameters. Now we just have to think a little bit. So it is not, so now we want to look at, to consider the edge weight parameters modulo the action of this group. Okay. But we have to be careful. This group does not act freely. So you have a one parameter family of elements in this group that will act as the identity. So now let's think about this, but this action is not free. For any lambda in infinity set, so S lambda by S lambda of V is equal to lambda if V is, let's say, white, and lambda inverse if V is black. Do you agree that this one parameter family of elements in this group will act as the identity, right? Each time you have an edge, you multiply by lambda and by lambda inverse. Okay, so this gives a one parameter family of elements of this group acting trivially. And you can check, it's easy, you have to assume that G is connected, but you can check that it's the only subgroup that is acting trivially. So, and since G is connected, it is the only one. So now let's count the number of parameters that we have when we look at edge weight modulo gauge transformation. So the number of parameters is equal to what? So I have number of edges minus number of vertices minus 1, right? Okay, so I will write this as minus number of vertices minus number of edges plus number of faces. And what do I have to add now? So I have to add plus number of faces, and then I have a plus 1. Okay, but we are in the plane, so this, well, actually on the sphere, this is equal to the Euler characteristic of the sphere, that is 2. And so we have number of faces plus 1 minus 2. That's number of faces minus 1. And we see that we have exactly the right number of parameters here. Okay. So it's the right okay. So it's a very simple but very nice trick, this idea. So you see, you have these edge weights, and you want to put them together in a way so that the weights you're going to associate to them are going to be invariant by this gauge transformation. And of course, it's true. You immediately think about multiplying these weights in some way, alternating like this, and it works. But you really need a bipartite structure. So in case the graph is not bipartite, I don't know a way of having a reformulation that gives you the right number of parameters. I don't know. Okay, so now I'm going to give you the only proposition of this little section. So the Dimer measure the Dimer model measure on a set of perfect matchings translates into the following measure on the set of height functions so the measure, I will write phi 0 here because it really depends on this unit flow that I had fixed of a height function h is equal to 1 over z product over all the faces of the corresponding volume weight power h f, where z is of course a sum over all height functions of this furthermore, this measure is independent of the choice of f0. You see, so it's very nice. You can really, if you have a biparallel graph on the plane, you fix phi 0, and then you have an injection, you have a bijection, let's say, from perfect matchings on the graph and some height functions. And when you translate the measure on dimers, on perfect matchings, it translates to the following measure on height functions. It's a measure that is very natural, that is given by these volume weights, and these volume weights are exactly the right number of parameters. Okay. And the proof is now going to be maybe 2 lines. Right, so for any phi like this, I want to extend my new beta that I had defined as, so I want to extend it multiplicatively, as I said. So it means here I take the product for e power phi e.
Excuse me?
Yes.
So you said that u phi 0 is independent of f0?
That's right,
So
yeah.
f0 is the phase that we set at 0?
That's right. You will see. So, I mean, I can already tell you. Here, if you change f0, if you take another one, it will change all the height functions it will add a constant to all of them. So you have an overall constant that goes in front, and so the overall measure does not change. You see?
The product of all QF is 1.
I'm sorry?
The product of all QF is 1.
Yes. So you mean it doesn't, the overall constant is 1, you mean? That's right, yeah. So you don't, yeah, you're right. In any case, it works, right? No, so she's right, of course. So if you add, I had said an overall constant goes in front, this overall constant is 1. So it's even better than, thank you. Okay, so for now, that's just a notation. And now let's do the following. So I have, so the measure on perfect matchings is basically given by nu of m. So the product of all the nus of all the edges. I want to take this and I want to divide it by one constant. So this will not change my measure on dimers, right? I just divide everything by nu beta of phi 0. This is a constant. So I'm not changing the measure on perfect matchings by dividing everybody by this same constant, okay? So now I can write nu of m as nu of phi m, nu beta of phi m over nu beta phi 0. Okay, this is just a notation. Again, nu beta of phi m is what? It is the product of, this will be always 1 or 0, of the weight of the corresponding edge. So this is just a question of notation. This works. Okay. Now this, I want to write it as nu beta of phi m minus phi 0. Again, it's really just the fact that I extended this nu beta in a multiplicative way. But nu m minus phi 0 is the boundary of hm. Right? Boundary of hm is of the form sum over e, hm of e times e. So this is nu beta of sum over e, hm of e. I'm sorry, this is a sum over faces. Sum over faces, f, boundary of f. And basically by definition of nu beta, here I have a product over all faces of of nu beta of boundary of f to the power hm of f. And by definition, this is the volume weight. So I get product f, qf, hm of f. And that's the proof. And again, this last line was already explained, and better it was explained by yourself actually. So here, this is because other choice gives h prime is equal to h plus some constant n, and so it does, and since the product over all qf is equal to 1, mu phi 0 is unchanged. Again, you don't need this fact that product is equal to 1, but it's even nicer, let's say. You all agree with this? So I think it's a very nice reformulation of the Dimer model, again, in case the graph is bipartite and planar. And I just want to take, so I have 5 minutes left, and I just want to just explain quickly how things change in the surface case. You can reformulate, it works completely fine in the surface case. So that the height functions might take periods, you know. So if you, again, the problem is you can define a height on the plane, and if you are on the torus, let's say, well, maybe if you go around a non-trivial cycle on the torus, you might get a height function that is, you know, that gets some, well, you might get a period when you go around it. And so actually you do need to take these periods into account as well, but it works. So let me, okay, so I will try to go fast and explain what happens in this case. So now assume that G, of course, is still bipartite, is embedded in a surface, so closed, connected, oriented surface sigma of genus G. So of course you can still fix some unit flow. And now for any perfect matching, consider phi m minus phi 0. You can look at this. And again, the whole thing works completely fine. It's in the kernel of delta 1. But now comes the problem. The kernel of delta 1 is not equal. It's not equal to the image of delta 2. Right. So here is the problem. You cannot, if you have these cycles, it doesn't mean they bound. Okay? Imagine again on the torus or anything. So you have to add a little something. In general, phi m minus phi 0, it belongs to the kernel of delta 1, which surjects onto h1 of the surface with real coefficients, which is of rank 2g. So it means that this cycle defines a homology class. Hence, we have a homology class of phi m minus phi 0 in this. And the problem is now we want to associate to this class really 2g real numbers. To this you need to fix a basis. So everything will depend on the basis. So there is no way around it. So we have to fix. So let's say a family. I will write them gamma of oriented cycles on the graph embedded in the surface, representing a basis of H1. And if you have this, it means that each time you have a phi m, you can look at the 2g numbers, real numbers, with respect to this basis. So then one can identify H1 with R power 2g, and each m gives 2g numbers. Let's say ai gamma of m in R, which we should think of as the periods. And so such that, so what I'm doing is phi m minus phi 0 is equal to the sum of okay, do I follow my notations? Yeah, maybe to have the notations right, I'll write everything like this. Okay, so when you have a perfect matching, you have associated to it 2g numbers and now what you can do is you take phi m minus phi 0 and then you also subtract all these numbers and then you'll have something which bounds. So hence, if you take phi m minus phi 0 and you also subtract am okay, this makes sense. So this belongs to the image of delta 2. So now we can play the same game, but we have to remember that we have these 2g numbers on top. So this is of the form boundary of H, M, which of course now depends on these gammas. Okay, I'll try to wrap it up. So of course we normalize it such that hm gamma of f0 is equal to 0. Okay, so hence, if I have m in m of g, it gives me a height function hm gamma and these periods am gamma 1, am gamma 2g. Okay, and so we can play the same game as before and try to reformulate the Dimer model so onto these models that now will consist, the states of the model are not only height functions, but it's height functions plus periods. Okay, so one can reformulate the Dimer model on the set height functions plus periods. So this requires, of course, the volume weights Qf, which was given by nu beta boundary of f, but also some new parameters. How do I want to write them? Qi is nu beta of gamma I. So it means that now if I count the number of parameters, I will get number of faces minus 1 plus 2g parameters, and you can check that that's still the perfect amount of the perfect number of parameters. So the number of parameters is therefore, what do I get? I get number of faces minus 1 plus 2g. And you can check, so you can make the same computation as I did here. You just have to change when the Euler characteristic, it's not going to be 2, but 2g minus 2, and 2 minus 2g, sorry, which is the right number of parameters. And then the measure is given by, so it's a measure that will depend on phi 0 and will also depend on this choice of the bases for the homology. And now I need to put as a state, as an input, I have the height function and these periods, and this will be given by, so product over faces Qf h of f times product over I of these new weights Qi power ai. So sorry, I went a little fast because I wanted to finish, but I didn't hide anything complicated here. You just look at the case of the plane and you exactly the same proofs just go through. And so of course, it's a little bit, it's not as nice as in the case of the plane. You don't only have a height function, you also have these periods, but at least it is a fact that you can reformulate everything with the right number of parameters and you can understand everything. You have the height and then you have the periods, so it's still kind of okay. Good, so that's the end of the class today. From next week on, I'm going to assume that the graph is toroidal, that is embedded on a torus. And then we're going to see that we have, in this case, we can solve the model in a very, very concrete and complete way. Have a nice week.